There we go. Okay, so sets, like I was saying, that we learned about in section 1.1, they're kind of the fundamental building block of math. They're the objects that we talk about. And logic helps us talk about the relationships between those objects. And propositions are the most basic kind. They're, well, let's just work through the definition. A proposition is a sentence, and usually in English, but also we'll be looking at math as well, so mathematical symbols. And it's a sentence that is true or false, but not both. Another word that you'll hear me use, and you might see written down in other places, is a statement. So a logical statement is another word for a proposition. And let's just look at a few sentences to see if we can get an idea of what propositions are. So in this example, I want to determine which of the sentences are propositions and which are not. Okay, so the first one, the sun is still up, so that kind of matters here. But it says the sky is blue. Is that a proposition? Is it true or false, but not both?
Yes.
Okay, good. And well, it's a little cloudy here, but I'm going to go ahead and call this a true proposition. The sky is blue. The second sentence here is Tulsa is the capital of Oklahoma. Is that a proposition?
Yes, but it's a false one.
Good. Yeah, Oklahoma City is the capital, not Tulsa. So this is false. But it is still a proposition. Good. What about number 3? Earth is the only planet in the universe with life. Anyone want to say whether that's a proposition or not?
It's kind of hard to say if it's true or false, but I think it would be a proposition.
Okay, good. So this is a proposition, but we don't actually know if it's true or false. So it is definitely one or the other. Either Earth is the only planet with life, or it's not. We just don't know. And that's perfectly fine. It's still a proposition. Okay, how about number 4? This sentence is false. Is that a proposition?
Yes.
Okay, so a proposition has to be true or false. Is this a true or false proposition? What do you think?
A true proposition because it's saying that sentence is false.
Okay, so
Oh wait, no, it's both. So it's
good. Yeah, you see the problem. Yeah, if it's true, if what the sentence is saying is true, then that means that it's not true because it says the sentence is false. So it contradicts itself. And if the sentence was false, well, that would actually make the sentence true because that would be the correct, right? So this is what we might call a self-contradiction, or just a contradiction. So it's not a proposition. Okay, and finally, number 5, sunsets are beautiful. Is that a proposition?
True.
Someone said it is a true proposition.
Can
It's
it be
not a
both if you
proposition.
just hate
Yeah,
sunset?
because
It's
it's
an
both true and
opinion,
false.
not really a true or false statement.
Okay.
That's it. I wouldn't
Yeah,
want
I mean, probably not many people would disagree with you that sunsets are beautiful, but maybe they just don't care about sunsets or something. Because this is definitely an opinion. So an opinion is something that people can feel one way or the other about, and it's not really true or false, it's just how they feel about it. So this is definitely not a proposition. Okay, and that's my last example. Probably you've thought of lots more as we've been going through this. I tried to find an example of each kind of sentence. So we have like a true proposition, a false one, and then there's a proposition where we don't know, and then there's a couple different kinds of not propositions. Can any of you think of another kind of sentence that is not a proposition? There's a big one that I left off my list. And it's something like a command. So if you tell something or someone to do something, like take out the trash, or do the dishes, or fold your laundry, they're commands. They're not true or false, so they're not propositions. Okay, so let's move along to what we call logical connectives. I don't think your textbook uses that word that I can recall. But a logical connective is a way to combine two or maybe more simple propositions to form something more complicated. The first one we're going to talk about today is a conjunction. But before I get into the details here, I also need to say something about this sentence here. So I said, let P and Q be propositions. And you're going to see this quite a bit. Instead of writing out a sentence every time I want to write a proposition, we're often going to use a letter, like in algebra where we use a variable, in place of a sentence, a written out sentence. So in algebra, you use something like X to stand for a number. In logic, we're going to use letters also, but to stand in for statements or propositions to be consistent. Okay, so let's take a closer look at the conjunction. The conjunction, well, that's just a fancy word for and. So a conjunction of two statements is just to say P and Q. And here's the mathematical notation for that. Instead of writing the word and, mathematicians usually use this symbol. It's something like an upside down V. Okay. So when is an AND statement true? Well, it works exactly like you expect it should. If P and Q are both true, then both of them have to be true. And if either one of them is false, or if both of them are false, then the AND statement, P and Q, is going to be false. Oops. I accidentally hit a button.
Can you go back to that other screen?
Yeah, I
All right.
accidentally hit a button on my camera. Okay, so we can write lots of examples. Here's one. 1 plus 5 equals 6. And the sky is blue. Okay, so this is a true mathematical proposition. 1 plus 5 is equal to 6. The sky is blue because the sun is still up, so that's also true. So overall, together, 1 plus 5 equals 6, and the sky is blue. This more complicated statement is also true. We can also make a false conjunction. So I could, instead of saying 1 plus 5 equals 6, I could say 2 plus 2 equals 5, and the sky is blue. So now instead of looking at a true statement conjoined with another true statement, we're looking at a false statement and a true statement. And so since this part is false, the overall conjunction is going to be false. Are there any questions about this idea of the and statement? I'll just wait a second because I think someone's still writing. Okay, let's move on to the next kind of logical connective. This one is called the disjunction. So the name kind of implies that it's the opposite of a conjunction. And this is actually the or statement in English. And in mathematical symbols, it looks like this. We flip the symbol for and to get the or symbol. And in mathematics, and as well as I think most computer programming applications, whenever you have an or statement, what you really mean is the inclusive or. So in the inclusive or, you mean both could be true or one could be true. It's not the either or, which means that only one of them is true. So the proposition P or Q is true when at least one of these is true. So you could have one true or two true statements together with the or. So you could have something like this. Tulsa is the capital of Oklahoma. Or 2 plus 2 equals 4. So what we're looking at here is a false proposition. And a true proposition. 2 plus 2 is equal to 4. So that means overall the statement with the or, Tulsa is the capital of Oklahoma, or 2 plus 2 equals 4. Overall, this is true. And something to keep in mind in logic, and this was a theme in the last example as well, you can use logical connectives like and or to combine statements that are completely different. Like whether or not Tulsa is the capital of Oklahoma doesn't have anything to do with math. But in logic, we're allowed to combine them together. Let's see. And just as an example of an inclusive or, we know that 1 plus 5 is equal to 6, or 2 plus 2 is equal to 4. This is actually a true statement because we're using the inclusive or. So in normal English, I think most of the time we mean the exclusive or. So if I would just said something or something else, then I would mean only one of them is true. But keep in mind in math and logic, we can have two true statements. And overall, our or statement would still be true. Okay, any questions over ands or ors?
That is really confusing, Professor. Just to want you to note that, honestly.
Which part?
So you're saying that the 1 plus 5 equals 6 is in conjunction, and 2 plus 2 equals 4 is still true?
Well, this is the disjunction.
Okay, disjunction.
I'm saying 1 plus 5 is equal to 6, or 2 plus 2 is equal to 4.
And all that matters is that one of them has to be right in order for it to be true.
Right, at least one of them. That's because we're using the inclusive or. Maybe I should write that somewhere. Okay, does anyone have questions or concerns about this one?
For me,
Uh-huh.
oh, you could have pointed out to him that the phrase "at least one"
Mhm.
that can also mean one or more.
Right, yeah. That's what I said earlier. The reason why it's confusing, I think, is because in English, when you use the word or, you're just speaking to someone. You probably mean the exclusive or, not the inclusive. So whenever we're doing math, we have to kind of change the way that we're thinking.
This is basically the computer science or.
Yes, yeah, exactly. Yeah, so if you have any experience programming, this is the or that you've used.
Are we going to be going over Boolean stuff, I thought, too? Or is that coming on later?
That'll be later.
Okay.
Boolean, I forget exactly what word the textbook uses, but that's where you're dealing with true and false things.
Okay.
And we are doing essentially that right now.
Yeah, that's what I wasn't sure if this qualified as Boolean or not.
It does. We're not going to call it that for a while, though.
Okay.
Yeah, anytime you're dealing with trues and falses or zeros and ones, you're probably talking about Boolean logic, or maybe you're talking
Yeah.
about binary. Okay, so the next thing that we're going to talk about are truth tables. And these are a way to deal with complex logical statements or compound logical statements and break them down into smaller pieces that are a little bit more manageable. So this is, roughly speaking, a technique to understand complex logical statements. And they're fairly self-explanatory once you've seen one or two. So the first thing I'm going to do is just explain kind of the general structure of what's going on here. At the moment, well, you just see 4 regions. And I'll start on the upper left here and tell you what's going to go in. So on the upper left, usually what we have are simple propositions. And when you're working with truth tables, you're probably going to have letters. So maybe I'll make one with three propositions, P, Q, and R. And over here on the upper right, you're going to have some sort of more complicated and the technical word is compound proposition. And just to fill one in, we're not going to complete the table for this particular one, just as an example. So I could have P or Q, and then I could have another kind of logical connective that we haven't talked about. This is called the implication. And maybe I have a not R and P over here. Okay, so we'll talk about this symbol at the end of today's lesson. It's the not symbol. Okay. So we have our simple propositions P, Q, and R, and those are the building blocks for this more complicated compound proposition. So all the letters are P, Q, and R. And you can have any number of propositions here. I've used 3. You might have 1 or 2 or 3 or 4, any number. Let's see. The next thing to talk about is the bottom right, or bottom left, sorry. Down here, we're going to fill in all of the possible truth values, all the possible combinations of truth values for these 3 propositions. So I'm already using this word truth values. The truth value of a proposition, it's kind of obvious what it should be. So a proposition can be true or false. So the truth value is either true or false for a proposition. Okay. And we have 3 statements, and I have to figure out what all the possible combinations are. Probably the first one you think of is where all 3 are true. We could also have maybe the third statement false. So that would be a true, true, false. And actually, any of these 3 could be false. So maybe I have a true, false, true, or even a false, true, true. So here I have 2 trues and 1 false in these 3 rows, but I could have 2 falses. Maybe I have true, false, false, but then I can move this true around to the other 2 positions. Maybe I have false, true, false, or false, false, true. Okay, and then there's one more possibility. We have 3 trues, 2 trues, 1 true. We could have 0 trues, so everything's false. Was someone saying something?
No.
No, okay. Okay, so for 3 propositions like this, you're going to have these 8 possible combinations of truth values. And what you would do next, and we're not going to do this right this second, but your next step would be to fill in the truth value for your more complicated proposition based off of the truth values of the simple propositions that make up this more complicated one. Okay, so that's the basic idea. Does anyone have any questions before we look at a more concrete example?
Just leave that up so for me to get that last.
Okay. Yeah, I can wait a minute. And one helpful hint that I can give you to make sure you have the correct number of combinations. If you count here, there are 8 combinations, and we have 3 simple propositions. And you'll notice that 2 to the 3rd power is equal to 8. So what's going on here is you're multiplying the number of possibilities. So 2 times 2 times 2 to get the total number of propositions. And if you have any number, maybe you have, I don't know, 20 simple propositions, you wouldn't want to do that ever by hand. But if you did, then this is how you would count. You would just have 2 to the n, where this number in the exponent is your number of simple propositions. So if you had 4 components here, you would have 2 to the 4, so that would be 18. Sorry, not 18. I was looking at that number. You would have 16 rows. So these tables can actually get really big really fast. Okay, so next thing on the to-do list is to make truth tables for the and the or statements, the conjunction and the disjunction. And I already told you in words what the truth values are, but now I want to make this table. On the left, we'll have to start by filling in all the possible combinations of two propositions. I've already filled in one row, so if both of them are true, P and Q are true, then the overall and conjunction is true. But if I have a false statement, if maybe Q was false, then the and would be false. And the same thing if P was false. So if I had a false true, the and statement would be false. Or if I had two falses, if P and Q are both false, the statement is false. Okay, so this is the basic idea. This is a complete truth table. On the left, we have our two building blocks, our simple statements, and on the right, we have the more complex one. And now we can move on. If there aren't any questions, we can move on to the or table. And as a hint to you guys, it's a good idea to be consistent in the way that you fill out your truth table. So if I fill out my truth table this way for two propositions, I want to fill out it the same way again. So I want to start with two truths, and then true, false, false, true, and false, false. And being consistent with this is just good practice to make sure you don't get mixed up. So if you filled it out one time this way, and you filled it out somehow else in the future, but you don't remember, that helps prevent that confusion. Okay, so when was the or statement true?
When at least both, or at least one of them is true.
Okay, so which rows does that correspond to?
The top three.
The top three, good. So these three. So we'll fill in trues there, and if both of them are false, there are 0 true components. That means the or is false. Okay, good. So you have the basic idea. Any questions before we do the last example? Okay, so the last example is actually our third kind of logical connective. It's the negation, and I already showed an example of it earlier. In English, we would say the word not. So if I want to negate a statement, I would say not whatever it is, so not P in this case. In mathematical symbols, we have this symbol, this character. You can think about it as maybe a sideways L or an elbow or something like that. And this is our not symbol. And this one works exactly as you think it would. If something is true and you say not whatever it is, then you switch the truth value. So the negation of a proposition has the opposite truth value, just like it should in English. So if P is true, and then I say not P, well, that makes it false. If P is false, and I say not P, then that means true. As simple as that. So I think I should do an example to finish off. So earlier we had the sentence, Tulsa is the capital of Oklahoma. And this is false. Maybe I call that my statement P. Then not P is a true statement. And in English, we would probably say Tulsa is not the capital of Oklahoma. So this is a true statement. Okay, are there any questions?
On the first, like, true or false graph, when you first introduced the truth tables, what did you put on the right side?
Oh, you mean the really complicated one? Yeah. This one?
Oh, fill in the corresponding truth values. Yeah, I was just wondering what that said, making sure I didn't miss anything.
Right. So
Yeah, but
just like
all
on
makes
the
sense.
example where we filled in.
Thank you.
You're welcome. Any other questions?
I got one about the homework, but I can wait till everyone's gone. Unless they want to hear me ask it. Not for this section, but the previous one.
Oh, okay. Yeah, let's just save that for after class. Okay, so if there aren't any other questions about section 1.2, that actually wraps it up. This is a much shorter section, thankfully, than the last one. So you guys can go ahead and leave and take a look at the homework. It's already up on Blackboard, and it'll be due a week from today. What is that, September 2nd? So go ahead and take a look at that when you get a chance, and then you can ask questions as they come up.
Is everything that we went over today, does that cover everything that's in the new homework?
Yes. Yep.
Okay. And
Well,
when will
you'll have to do some thinking, of course, but
okay. When will you be uploading this video? Just because I like to just review where I'm doing homework.
I'll upload